Now in section 1.5, we'll be talking about exponential functions. Now the function f of x is equal to 2 to the x is called an exponential function because the variable x is the exponent, and it should not be confused with the power function g of x is equal to x squared, in which the variable is the base. So in general, an exponential function is a function of the form f of x, which is equal to a to the x, where a is the positive constant. Okay, now there's graphs of members of the family of the functions y equals a to the x, which are shown in figure 3 for various values of the base a. Now notice that all these graphs pass through the same point, which is 0, 1, which is the y-intercept. Because a to the 0, anything to the 0 power, is going to equal 1 for the fact that a does not equal 0. Now notice also that as the base a gets larger, the exponential function grows more rapidly for when x is greater than 0. So if you take a look at the base here, right, here's 1.5, there's 2 to the x, 4 to the x, 10 to the x. So you can see it's increasing, okay, faster. And then the fractions are the bases. So when the fractions get smaller, it's decreasing faster. So here, what it's saying that if a is in between 0 and 1, then a to the x approaches 0 as x becomes large. Now, if a, meaning the base, is greater than 1, then a to the x approaches 0 as x decreases through the negative values. So in both cases, the x-axis becomes the horizontal asymptote. Okay, and we'll go over more of this in section 2.5. Now, you can see that from the figure 3 that there are basically 3 kinds of exponential functions, y equals a to the x. Now, again, you can see that, again, a is in between 0 and 1, where the function is decreasing. So you would want to make note that it's decreasing when a is in between 0 and 1 for the base. And then if a is greater than 1, then we know that it would then be increasing, or an increasing function. Exponential function, that is. Now, we observe that if a does not equal 1, then the exponential function y is equal to a to the x is going to have the domain of r of all real numbers, and the range goes from 0 to infinity. So we can say that the domain is such that x is all real numbers, and the range goes from 0 to positive infinity. And then if you notice that if we take a look at these graphs where you have 1 over the value of 2 or 1 over the value of 4, the graph of that function is just a reflection of the graph of y equals x about the y-axis. So these are basically, okay, this is the 4 to the x, and 1 over 4 is the reciprocal, so therefore it's a reflection according to the y-axis. 1/2 to the x, same thing with 2 to the x, again, is a reflection of each other. Okay, so if you look at figure A, okay, you can see here that it's a decreasing function because a is in between 0 and 1, meaning that it's a fraction or a decimal. Over here, when the value is 1, then it's a horizontal line. And then over here, when a is greater than 1, you can see how it is decreasing. Okay, so one reason for the importance of the exponential function lies in this particular property here. And what it's saying here is that if x and y are rational numbers, then these laws are well known from the elementary algebra. So it can be proved that they remain true for arbitrary real numbers. So here are the laws of exponents. If you have a to the x plus y, then it's equal to a to the x, a to the y. you would have multiplied these two together and you would add the exponents in reverse. Same thing here, a to the x minus y is equal to a to the x over ay. A to the x to the y, which is the power rule, is a to the xy, and ab to the x is a to the x times b to the x. Now, when you're reflecting and shifting an exponential function, we want to sketch the graph of the function where y is equal to 3 minus 2 to the x and determine its domain and its range. Now, first, what we're going to do is we first need to graph this y equals 2 to the x. And again, we know the y-intercept is 1 and it's an increasing function. So this is the basic function for y is equal to the x. Now, then we see that we're subtracting that. So what that means is that we are reflecting the graph when you're subtracting here about the x-axis. So now it flips according to the x-axis. Then what we do, and since we shift the graph now, since we're adding 3, we're going to shift it now up 3 units. And therefore, that gives us the graph of y equals 3 minus 2 to the x. And then we can say that the domain of this function, okay, still is that x is all real numbers. Now, the range, okay, starts at the value of 3, or actually it ends at the value of 3. And so it begins at negative infinity because it is decreasing. So therefore, it starts at negative infinity and then goes all the way to the value of 3. Now, because y equals 3 is a horizontal asymptote, that means it doesn't touch. So we know that it's negative infinity to 3. Now, for example number 2, okay, we have an exponential function versus a power function. So using a graphing device to compare the exponential function f of x is equal to 2 to the x, and the power function g of x, which is equal to x squared, which function grows more quickly when x is large? So when you graph these two functions on the same graph, the one in blue represents the parabola y equals x squared. The one in red is y is equal to the x. Now, if we expand the window, you can see clearly that the exponential function is increasing much faster. So again, both functions in figure 6 graph using that window from negative 2 to 6 and 0 to 40. Okay, we see the graph intersects here at 1, 2, and then 3 times. Okay, but for when x is greater than 4, the graph of the function y equals 2x is now above the graph of y equals x squared. So here is where x is 4, and anything that's greater than that shows that this graph is above y equals x squared. Now in figure 7, it gives more of a global view and shows that for large values of x, the exponential function y equals 2 to the x grows far more rapidly than the power function or the parabola y is equal to x squared. Now in example 2, it shows that y equals 2 to the x increases more quickly. So to demonstrate just how quickly it increases, we perform the following thought experiment. Suppose we start with a piece of paper 1/1000th of an inch thick and we fold it in half 50 times. Now each time we fold a paper in half, the thickness of the paper doubles. So the thickness of the resulting paper would be 2 to the 50th over 1,000 inches. Now how thick do you think that is? Well, it works out to be more than 17 million miles. Now we're going to deal with some applications of exponential functions. Okay, the exponential function occurs very frequently in mathematical models of nature and society. So what we're going to do is we're going to go through an example 3, that gives us an idea of how this works within society here. Now, the half-life of strontium-90 is 25 years. This means that half of any given quantity of strontium-90 will disintegrate in 25 years. So what we want to do is we want to answer the first part of this question. So it's saying that if we have a sample of strontium-90 has a mass of 24 milligrams, find an expression for the mass m of t that remains after 10 years. Okay, so what we want to do is we first want to figure out what happens when it's at 0. So at first, when we plug in the time m at 0, well, the initial tells us that it has a mass of 24 milligrams from that first part of the sentence. Okay, and then what happens when it's at year 25? Okay, so since we're talking about a half-life, we're going to take half of that 24. But we know that half of 24 is going to give us what? It's going to give us 12, right? But we don't want to look at that. We want to look and see what happens exponentially. So now, if we double the years, and now go from 25 to 50, well, if we're doubling that, that means we have to multiply it again by 1/2. So we have 1/2 times 1/2 of that 24. And if we want to write this in exponential form, this would be 1 over 2 squared times 24. Okay, now if we want to increase it again for another 25 years, well, that is m of 75. So what do you think we're going to have to do here next? Well, that means we're going to take 1/2, multiply it by 1/2, multiply it by another 1/2 times 24, which would then equal 1 over 2 cubed times 24. Okay, and then let's go to 100. So if we go to 100, then I think we can assume what's going to happen next, which means we're going to end up getting 1 over 2 to the 4th power times 24. Okay? So, from this pattern, we can see that it appears that the mass of the remaining years, t years, becomes the following. We would end up with m of t, which is equal to 1 over 2 to the power of t divided by 25 times 24. And so if we want to write this without a fraction, then we can start using our exponent rules. So this would be the same thing as saying 24 times the base of 2 to the negative power of t over 25. And so now, if we want to write this so that we have our exponent is just our variable, so we would have 24 times 2 to the negative 1 over 25 raised to the power of t. Now, if we want to find the mass remaining after 40 years, we want to find it correct to the nearest milligram. So that means that we're putting in the year now for 40. So t now is going to equal 40. So now using our model to be able to predict what that would be, we would have m of 40 which then equals 24 times 2 to the negative 40 over 25. And that gives you approximately 7.9 milligrams. Okay? So now we want to be able to use a graphing device to be able to graph and estimate the time required for the mass to be reduced to 5 milligrams. So let me go ahead and find this graph so I can put it into our notes here. Okay, so as you can see here, using our windows, right, our minimums and maximums for x and y, we have our x minimum is 0, the y is 100, the y minimum is 0, and the y max is 30. So when we use the graphing calculator, we also graph the line m is equal to 5. And so by graphing the line, m is equal to 5. So we have our graph of the first function. So let's go ahead and do that. I'm going to go ahead and put that in my calculator here. Okay, so let's go ahead and put in the window of our function, of our view of our rectangles. So we have 0 and 100. And there's our scale. We have 0 and then 30. So now if we put in our graph, so this is 2, 2, and put in parentheses, negative 1 divided by 25, parentheses, and then we're raising that to the power of t, or we can just put x. And then in our second equation, we want to put m is equal to 5 since we want to find out the mass for it to be reduced to 5 milligrams. So we're going to put in 5, and then we're going to graph. So now once we graph, what we want to do is we want to find out, okay, what's happening right here? Okay, so again, what we can do is we can come over here and trace and determine, okay, what's happening at that intersection. So we keep going, keep going, keep going, keep going, keep going. So right about there, we can say that it's intersecting. So remember that the horizontal axis is representing the time. And so x represents about 57 years. So by looking at the graph, we can say that t is approximately 57 years. Okay, then we have the number e. Now, of all possible bases for an exponential function, there is one that is most convenient for the purpose of calculus. Now, the choice of a base a is influenced by the way the graph of y equals a to the x crosses the y-axis. So if you look at figures 11 and 12, it shows the tangent lines to the graphs of y equals 2 to the x and y equals 3 to the x at the point 0, 1. Now here, there's a tangent line here, it's in red, and this one's in red. Okay, now tangent lines are going to be defined more precisely when we get to 2.6, but it's important that we're going to know that for calculus. So for present purposes, you can think of the tangent line to an exponential graph at the point as the line that touches the graph only at one point, meaning right here. Okay, now if we measure the slopes of these tangent lines at 0, 1, we would find that the slope of this tangent line is approximately 0.7. So this slope is a little different here, right? Now if you look at this function, y equals 3 to the x, now this slope is approximately 1.1. And for y equals e to the x, well, what's nice about that slope? Well, that slope is 1. Okay, so we call the function f of x equals e to the x the natural exponential function. So what will happen is that when we get to chapter 3, okay, that some of the formulas of calculus will be greatly simplified if we choose the base a to the slope of that. So the slope of the tangent line when y is equal to a to the x at 0, 1 is going to be exactly 1. Now, in fact, there is such a number, and it is denoted by the letter e that we just saw, right? And this notation was chosen by the Swiss mathematician Leonhard Euler in 1727, probably because it's the first letter of the word exponential. Okay, let's move on to example number 4. Okay, here we're talking about transforming the natural exponential function. So we want to be able to graph the function 1/2 e to the negative x minus 1 and then state the domain and the range. So we start with the graph of y is equal to e to the x, which is in figure 15. So again, that is the normal basic function for the exponential function of base e. Okay. And then what do we know? Well, we know that the value of x is negative. So since the value of x is negative, then we reflect about the y-axis to get the graph of y is equal to e to the negative x, which is in figure B here. Okay. Now again, notice that the graph crosses the y-axis with a slope now of -1. Then what we're going to do is we're multiplying it by a value of 1/2. So we're going to compress the graph vertically by a factor of 2 to obtain the graph of y is equal to 1/2 e to the negative x, which is in this graph here. And then finally, we shift the graph downward 1 unit because we're subtracting 1 to get the desired graph here. So again, we want to be able to find a domain and range. So the domain is, again, x would represent all real numbers. And then what is the range? Well, the range starts at the horizontal asymptote of -1. So it starts at -1, and then it goes all the way up to positive infinity. Okay, now for our last example here, exponential functions get big fast. So using a graphing device to find values of x for which e to the x is greater than 1 million. So in figure 16 here, in this figure, we graph both of the functions y is equal to e to the x and the horizontal line y is equal to 1 million, which is y is equal to 10 to the 6. So this is y is equal to 1 million. Now we shall see that these curves intersect, meaning here, okay, when x is approximately 13.8. And that's down here. Thus, if e to the x is greater than 10 to the 6, when x is greater than 13.8. Okay, so let's write that down here. So we can say that the function e to the x, when it is greater than 1 million, right, or 10 to the 6th, then what does that tell us? That tells us when x is going to be greater than 13.8. So anything above 13.8, that means that e to the x is going to be greater than that horizontal line. So it is perhaps surprising the values of the exponential function have already surpassed 1,000,000 when x is only 14.